Hello everyone, welcome back to this little series where we're gradually exploring some basics of how computers work. Today we're going to be taking a little look at 7-segment displays to help us visualize some stuff in our project. So I have things wired up here so that we can flip these tiny switches to light up this decimal point, and each of these 7 individual segments as well. Then of course, as we're all familiar with, we can power up different combinations of these segments to display any of the 10 decimal digits. This is going to be really helpful over in our simulation, where last time we'd just finished creating a 4-bit register, capable of storing every whole number from -8 all the way to +7. Now, for a super quick refresher on negative numbers in binary, let's say we have the value 1101. We know that the weight of each bit goes up in powers of 2, so this is the 1's place, this is the 2's place, 4's place, and 8's place. So to convert from binary to our more familiar decimal number system, we'd just do 8 times 1, plus 4 times 1, plus 2 times 0, plus 1 times 1, equals 13. To support negative numbers though, we can use the 2's complement representation, which simply assigns this most significant bit a negative weight, so this becomes -8 over here, meaning instead of 13, we end up with -3. Alright, so back to our little register here, it would be very nice if we could see what value is currently being stored in there. To help with this, I have added a simple chip library to the simulator, where we can now find a 7-segment display. Instead of the usual decimal point though, I thought it'd be more helpful to us if this one had a negative sign over here, which I guess makes it more of an 8-segment display, but anyway. The problem we face now is that, as we've seen, the inputs to this control each segment individually, but what we'd really like is to be able to just give it a 4-bit number and have it automatically light up the correct segments for us. To build that behavior, we're going to first need a truth table. We can start by listing out all the possible 4-bit inputs, and let's also note down the decimal values that we want to display for each of those. Then we just need to figure out which segments need to be lit up in each case. So to show a 0, for example, we can see that all the segments apart from G and the negative sign should be on, so we can write that out over here. We can then do the same thing for 1, and for 2, and so on. This looks a bit intimidating though, so before we try to build it out of logic gates, we should first simplify it as much as possible. Let's worry about one segment at a time. So the sign segment, for example, is extremely easy. It just correlates exactly with the most significant bit in our input. Let's move on then to segment A, which looks a bit scarier, but an important thing to realize is that we can choose to think about either just the 1's or just the 0's, and in this case there's far fewer 0's being output, so let's focus on those. All we need to do now is design some logic that results in 0 only when given one of these 4 input cases. So starting off with the first case, we first need some logic operation that will give us a 0 only if these 3 bits are all 0. An OR operation will do that, so let's quickly write this out in Boolean algebra form, where the plus sign represents OR operations. Then to finish off this case, we can see that the least significant bit here must be 1, so we can simply use a NOT operation to invert that bit, shown with this little bar on the top, and then OR it with the rest of them. Repeating this process for the other 3 input cases, we end up with these 4 expressions. So now, if we're given any input value, let's say 1100 for example, then without consulting the truth table, we can figure out what the output should be by evaluating all of these. Let's do this first one quickly. So we substitute in the input values, and then we can see this 0 is inverted, so let's flip that to a 1, and of course 1 or 0 or 1 gives us 1. If we do the same thing for the second expression, we get 1 again. And then for the third expression, we have 0 or 0 or 0 or 0 is 0 this time. And finally, the last expression comes out as 1. Now, what does this all mean? Well, if we sneakily peek at our truth table, we can see that the inputs we were given in this example match this input case here. which means the output should be 0. No surprise then that the expression designed specifically for that case resulted in 0, whereas the others all came out as 1s. From this, we can realize that so long as one of the expressions works out to 0, then the overall output for this particular input should be 0. So that means that we now need some logic operation that will give us 0 if any of these expressions evaluate to 0, and for that, the AND operation will do the trick. So let's combine our 4 expressions by ANDing them together, which is represented as multiplication, since multiplying anything by 0 also gives 0. We now have this big equation for our output, and we can try to simplify it using the rules of Boolean algebra. For instance, just like regular algebra, we can take out common factors, and we can spot a nice pair of those over here and here, meaning we can rewrite all of this like so. From that, we end up with this rather pointless statement, A or not A, which is just always going to be 1 no matter what, and so we can replace it with a 1. But of course, ANDing anything with 1, just like multiplying anything with 1, has no effect on the original thing, and so that can actually just be removed entirely. There are a bunch of helpful rules like this. For example, if you're doing an OR operation on a bunch of inverted variables, that's the same thing as taking the non-inverted variables, ANDing them together, and then inverting the result. In other words, an AND operation. I don't think that's making much difference here though, so I'll leave it how it was, and let's now try building this logic in the simulation. For convenience though, I'm going to start out by making a 3-input OR gate, simply by chaining 2 OR gates together. And then we can use that, along with our regular old 2-input OR gate, to make a 4-input OR gate. Alright, with that out of the way, I'm going to bring up our equation here, and let's start by setting up inverted versions of all of the inputs. Then, following the equation, we'll need 3 OR gates set up like this, and into the first one goes the inputs A, B, C, and not D. Into the second one goes not B, C, and D. And finally, into the last one, we just have all the inverted inputs. We now just need to AND the results together, and I forgot to make a 3-input AND gate, so we can just construct one here. Okay, time to see if this actually does what it's supposed to do. We'll need to use our imaginations here to fill in the blanks, but for a 0, segment A should be on, so that's good. Then for a 1, it should be off, which we can see that it is. And for 2 and 3, it should be on again, but it should turn back off for 4. So far so good. I'll continue testing this in the background, but it looks like our algebra has worked out, and so we could of course repeat this whole process for all the segments to get a fully working display. There is also something called a Carnot map, which is essentially a visual way of doing the same Boolean algebra simplification, and it can definitely make the process a lot less painful. For today though, I just wanted to get a sense of how we could figure something like this out by ourselves, but what I'd actually like to experiment with now is some computer-assisted design. So I've spent several hours writing this very crude little program where we can input a truth table, tell it what gates it's allowed to use, and then ask it to find a solution for us. I haven't fully tested it yet though, so let's start with something simple like an exclusive OR operation, where the output is only on when just a single input is on. Then I'm going to forbid most of these gates here, especially the exclusive OR gate, that'd be a bit too easy, and let's see what it comes up with. It has immediately printed out a solution over here, and to make sure it's not bluffing, let's build that quickly in the simulation. So it just wanted 4 NAND gates with the inputs wired up to the first 3 like this, and the output of the first NAND gate going to the next 2, and their outputs going to the last one, which gives us our final output. Alright, so with both inputs off, the output is off, then with just one input on, the output is on, and finally with both inputs on, the output turns off. So that's perfect. Let's head back to the solver program then, and try pasting in our giant truth table for the 7-segment display. I'll allow it to use all these different logic gates this time, and let's see how it goes. This might take a while. Alright, the program has finally finished running, so I'm going to just follow its instructions to build this thing. Its only goal, by the way, apart from finding a valid solution of course, was to try use as few logic gates as possible. It ended up with 19 in total here, which is definitely a lot fewer than anything I'd have been able to figure out, because simplifying the logic for each output individually is fairly straightforward, but trying to figure out all the places where you can reuse some of the logic from one output in the calculations for another output can get ridiculously difficult. But while using fewer logic gates is nice of course, there are many other factors to consider if you're making something in the real world. For example, we've talked before about how each gate introduces a tiny delay, and so the more of them that are chained together in a sequence, the longer that overall delay will be. So a better design might actually use many extra gates, but prioritize having things run more in parallel. Anyway, let's test if this thing actually does what it's supposed to do. It is showing a 0 currently, which is a promising start at least. So I'll then turn this input on over here, and now it's showing a 1. Alright, next comes 2, then 3, and then 4. Looking good. Let's then test 5, 6, and 7, and it should then flip over into the negative numbers, starting with -8, then -7, -6, -5, -4, -3, -2, and -1. So it seems to work. We should probably save it then, and let's just call it something like digit display. While I was wiring this all together, I started wondering what kind of design a different solver might come up with, and so just for fun, I'd like to quickly try this free one I stumbled across called Logic Friday. We can import our truth table in here, and then ask it to map that to logic gates. I'll then choose some settings quickly, and let's see if this also needs over an hour to solve the problem. No, not even a second. It does seem to be using a few extra gates though, so I'm not sure if there are some other constraints it's following or why that is, but I still found it interesting to see what it came up with. Anyway, let's head over to reality for a moment, because I always enjoy playing around a bit with real-world components as well. This little chip takes in a 4-bit input, and like what we've been doing, it decodes that for the purpose of driving a 7-segment display. If we take a look at its datasheet, we can see that it supports the digits 0 through 9, and for the remaining spots it looks like it wasn't designed to do anything in particular. Then we've also been given this logic diagram in case we want to get a very rough idea of what's going on inside. So up in the corner we can see the 4-bit input, and then there are some extra inputs like this ripple blanking, which we'll see later is helpful when chaining multiple displays together. But we can see over here that the outputs for the segments are just handled independently by a handful of gates each, which looks a lot more like when we're trying to solve the problem ourselves than the convoluted mess my program came up with. Anyway, I've been wiring things up so that we can try it out quickly. We'll just need to slot our components in and turn on the power. We do now have a 0 on display, but it's not showing up very well on the camera, so I'll plunge us into darkness, and that's a lot easier to see. Alright, let me fight with these fiddly little switches to try input a 1, and a 3, and a 7. I won't test all the combinations, but let's take a look at 8 and 9 as well. Okay, so I thought it was nice to see this real-life version in action, but let's hop back inside the simulation now to start making some use of our virtual one. I'm going to go over to the chip library and open up the 4-bit register we built last episode, and we can then just add in our little display here to show what value the register is currently storing. So I'll finish wiring this up quickly, and then let's try it out by entering some data over here. We'll then need to turn on the store signal, and nothing happens yet because remember we built this to be synchronized with the clock signal. So only when that switches from low to high will the value actually be stored, and we can see it showing up on the display now. Alright, so this is perfect for visualizing the data inside of our minuscule 4-bit registers. And originally my plan was to stop here because we're going to be playing around at the 4-bit level for a little while still. But in the future we're definitely going to want to upgrade to 8 bits at the very least, so I think we might as well actually get our display ready for that eventual upgrade now. In that case, not being able to display the digit 9 is a bit of a problem, so back to the drawing board I guess. I'm going to make a new 7-segment truth table, this time with the outputs just mapped to the digits 0 through 9, and then after that the rest of the spots are marked with X's, meaning don't care. So just like that real-world chip we saw a moment ago. In fact, we could even just copy its design, but I'm curious to see what my little program comes up with if we leave it to ponder this problem for a while. In case anyone's interested in how the solver works, by the way, it's super simple. It just makes loads of completely random designs and then selects the best ones from those and makes small tweaks to them, such as adding or removing a random logic gate or connection. Then that just repeats over and over in a kind of evolutionary approach. I'm not sure if this is a good technique for this problem. My implementation at least is certainly horrendously slow, but it seemed like the easiest thing to get up and running. Alright, I've finally finished wiring this all up, so let's go test it quickly. Here we have 1, 2, and 3 working well. Then here's 4, 5, 6, and 7. And finally, let's check 8 and 9. Very nice. Something I found kind of interesting is that almost all of the don't care states for this wound up actually being valid digits. I suppose it makes sense since the logic is so condensed, but I was still surprised to see it. Anyway, I'm going to actually delete the display from here and instead add 7 output pins, which we can just connect up quickly. Then let's save this and call it our 7-segment driver or something along those lines. And then going into our old digit display chip, I'm going to ruthlessly delete everything in here and replace it with this new version we made. Alright, so now that we have all 10 digits at our fingertips, let's take a look at this 8-bit input that I've set up over here, which can represent the numbers from 0 to 255. Or if we're using 2's complement, then from 127 down to negative 128. But let's forget about negative numbers for a moment, and say we have the input 11000011, for example, which is 195 in decimal. The challenge we face now is somehow displaying that number across 3 of our digit displays here. Essentially, we need to take that input binary value and break it down into 3 4-bit values, representing the individual decimal digits 1, 9, and 5. This representation is called binary coded decimal, by the way, and to figure out how we're going to do this conversion, let's start by looking at a single BCD value. This, as you might expect, represents the decimal digit 0, and let's just count upwards. So this represents the digit 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that we have a problem, because there is no digit 10, of course, but our 4-bit binary number can go all the way up to 15. So what we want to do is somehow force this binary number to run out of space or overflow at the same time that we run out of decimal digits. To do that, we could simply add 6 once we reach 10, because 10 plus 6 gives us 16, and with just 4 bits that overflows to 0. In that case, of course, we'll want a second BCD value over here to record the full number. So combined, these represent 16, but more importantly to us here, taken individually, they represent the digits 1 and 0, which we'd read as 10. Let's look at another example quickly. This time we have 1101, which is 13 in decimal, so again, not a digit. As we figured out a moment ago though, we can fix this simply by adding 6. That overflows this BCD, so we'll need another one to store the full number, and we're now being told to display the digits 1 and 3, which of course we'd read as 13. This idea of adding 6 is the key to a clever little algorithm called Dabble, which is going to allow us to actually do this computation for however many digits we need. So let's say our inputs are 1011 this time, which is 11 in decimal. With any 4-bit input, we'll need at most 2 BCD values to store the result, so let's set those up over here already. We then want to move the input bits into those BCDs, so let's begin by just taking all the bits we have and shifting them over one place to the left. So we now have a value of 1 in here. Let's then do another left shift, which doubles this value to 2. We can then do yet another shift, which doubles the value again, except this time a 1 also got shifted in from the input, so in total we now have 5 in here. Now, once we reach a value of 5 or more, we know that the next left shift is going to at least double that and give us an invalid BCD value, meaning we'd have to then use our trick of adding 6 to fix it. Alternatively, before we double everything with the left shift, we could just add half of 6, which will of course amount to the same thing in the end, but it's a bit easier to implement, just because we won't have to worry about things overflowing right away and having to then carry one to the next BCD. So adding 3 here gives us 8, or 1000 in binary. Now only one of the original input bits is remaining here at this point, so we're going to do a final left shift and the algorithm is now complete, giving us the correct digits, 1 and 1, to make up 11. So that's the double algorithm, double referring to the left shift, and dabble referring to how we sometimes have to interfere by adding 3. Alright, I think we're finally ready to try tackling this 8-bit example we started out with. So we have 11000011 as our input, which we know is 195 in decimal. Any 8-bit number is going to have at most 3 decimal digits, so let's set up 3 BCD values over here. Then we can do our first left shift, and a second one, and a third one. We'll need to stop for a moment now though, because we have a 6 over here, and remember if it's 5 or greater, then we need to add 3. So let's do that. We can then shift everything over to the left again, and there are no problems here, so let's shift once more. And once more still. We now have 8 in here, so plus 3 again, and then shift it all over. Here's something new though, we now have values greater than 4 in 2 places at once. But we can just handle them individually, plus 3 over here, and plus 3 over here. There's only one of our original input bits remaining, so this is going to be the final left shift. And there we have our answer, 195. Pretty cool. We now just need to implement this with logic gates. I've started out by writing a Dabble truth table over here, so you can see the entries up to 4 are unchanged in the output, but then from 5 to 9, the outputs have all had 3 added to them. And finally, we don't care about the remaining states, since we always avoid those with our preemptive dabbling. Now, we could build this behavior using the 4-bit adder we created a while back, along with some extra logic. But I decided to outsource the thinking again to my solver program, which I'm not going to make a habit of in future videos, but for today I've been enjoying seeing what it comes up with, and we have enough other stuff to worry about. Let's quickly verify that this actually works though, so the output should be the same as the input for 0, 1, 2, 3, and 4. Then 5 should give us 8, 6 should give us 9, 7 should be 10, 8 should be 11, and finally 9 should be 12. Looks good to me, so I'll go save this quickly, and let's just name it Dabble. Okay, with that made, we can start implementing the algorithm. So we have an 8-bit input here, and we need to output the 1's place digit, the 10's place digit, and the 100's place digit. To figure this out, I'm going to bring up our visualization, but instead of actual 1's and 0's for the inputs, I've given them names, because we want to try figure out a general solution. Now, we can safely do 3 left shifts at the start, but after that, this value here might be greater than 4, so we'll need to bring in a Dabble chip to deal with it. And I'll wire up the inputs A, B, and C. Then to help us keep track of things, I'm going to give this chip a label, maybe just the letter T for example, and so its outputs are then T0, T1, T2 and T3. And whatever values those are, that's what we're now going to have in here. We can then left shift again, and now these are the inputs we'll need to feed into the next Dabble chip. So hopefully it's making sense already how we can just keep track of what goes where, and as long as we're careful about it, it should be pretty smooth sailing. Alright, I'll call this chip over here U, and we can update the visualization with its output values. Everything then shifts to the left, and we can grab another Dabble chip and connect up U2, U1, U0, and E. Let's then follow the alphabet and call this chip V, and again update the visualization with its outputs. Now after this next left shift, we could potentially have a value greater than 4 in the tens place as well, so we're going to need to use 2 Dabble chips this time, and I'll go ahead and wire those up quickly. Alright, let's name these two W and X, then update the visualization as always, and we can see we'll need another 2 Dabble chips to handle things. So I'll fast forward through some more wiring. And then let's call these last 2 chips Y and Z, and for the final time update the visualization. We can now simply look at where everything has ended up, and follow that to connect the final outputs. Okay, let's see if this works. I'll try putting in that 11000011 from earlier, which should be 195, and taking a look at the outputs, we do have a 1 in the hundreds place, a 9 in the tens place, and a 5 in the ones place. So it looks like we've managed to successfully hardwire the double-double algorithm into our little chip here. Let's now use this new chip to control these 3 displays we have. So I'll wire up these inputs quickly, and then we can connect the outputs up to those digit displays. Alright, let's test our favorite number, 11000011, and there we finally have 195 proudly on display. I'm finding all this bright red a bit overwhelming though, so I'll maybe change the color of our wires to green instead. So we're very nearly done at this point, but there are some small details that I'd still like to work out. For example, if we turn off this input up here, we now have the number 67. But there's this leading 0 which is a bit pointless and distracting, and ideally that would just be blank. Or say we're showing the value 3, then both of these displays should be blank. So let's open up our digit display and add a new input pin here called ripple blanking. When this is on, the display should turn off rather than show a 0. So we can test if the input is 0 using our 4-input OR gate to first tell us if any of these inputs are 1, and if that's not the case, then we know they're all 0. Let's then AND that with the blanking signal, meaning that when this pin here is outputting 1, the display should be off. I think it makes more sense if we invert that though, so that 1 means on and 0 means off. We can then intercept these signals going to the 7-segment display, and just add in a bunch of AND gates so that we can turn them all off whenever we want. I'll just quickly finish wiring these up again, and if we now turn the blanking signal on, then we can see that the display switches off. That should only be the case when the input is 0 though, so let's test if we put a 4 here for example, then the display does light up anyway. Okay, but say we do have a 0 and the display turns off, we'll then want to inform the next display in the sequence that it should also turn off if it's showing a 0, which is the ripple part of ripple blinking. So we'll just need to add an output pin here so that the signal can continue on its journey. Returning now to our 3 displays here, I'll add in an input to enable this blanking functionality, which we can wire up to the first display, and then that should ripple over to the next display. Then if we had more than 3 displays, this would continue rippling along, but we always want the last display to be on, so I'll just leave this disconnected. Alright, let's then enable the ripple blanking, and now we have just a single 0 lighting up, which looks a lot cleaner I think. Then if we display say 15 for example, we can see the second display comes on, and if we go up into the hundreds, then all 3 displays will be on. All that I want to add now is support for negative numbers, which shouldn't be too much work. We mainly just need to make a chip for negating an 8-bit number, in other words making a positive number negative or a negative number positive. We figured out back in the first episode that this requires 2 steps, first flipping all of the bits and then adding 1. Flipping the bits can obviously be done with NOT gates, but if we use exclusive OR gates instead, then we can easily have an enable signal to control whether we actually want to perform the negation or not. Finally, to add 1 to the result, we can just cobble something together quickly using 2 4-bit adders, and we should use the enable signal as the carry-in, because we only want to add 1 if it is enabled. This is pretty much the exact same thing we did to handle subtraction when we are creating our simple ALU. Anyway, let's try this out quickly. So for example, this here is the value -1 in 2's complement, and with the enable turned off, we just get the same thing at the output. But if we now enable this, then negating -1 gives us +1 at the output. This is going to be helpful because we don't have any way of telling the Dabble chip we built to interpret a number using 2's complement. So for this input, it would always just display 255. If we wanted to display this input as -1 though, then somewhat counterintuitively we'd need to negate it so that it gets interpreted as +1, and then we can just slap a negative sign on that. So back here with our 3 displays, I'll add an input to control whether we want to use 2's complement or not. So if that's on, and this is a negative number, then we'll want to grab our new negation chip and enable it. Then I'll quickly connect this all up again. And now let's try 11111111 as our input, which shows up as 255 of course, but then if we turn on 2's complement here, now it's showing as a 1. So that's perfect, we're just missing the negative sign. To address that, let's make one last edit to our digit display and add in an input for lighting up that negative sign. We definitely wanted to respect the ripple blanking signal though, so we can just use another AND gate to deal with that. Then, of course, if the negative sign is supposed to be on, but gets disabled due to that blanking signal, which we can test for quickly over here like this, then we'll want it to show on the next display instead, and we can just use the same ripple concept again to make that work. Back over here then, let's grab this signal which tells us if we're dealing with a negative number, and feed that into the negative sign input of this digit display. Nothing's showing up because this display is blank of course, but it can pass the message along to the next one, and it can do the same, and in the end we'll get our -1. So, just to test and review what we have here, we can switch between unsigned and 2's complement representations. We can disable ripple blanking, which looks terrible, let's not do that. And of course we can display all of these 8-bit numbers thanks to the Dabble algorithm, and also thanks to that chip we made earlier of course, that actually drives the 7-segment display based on the given binary coded decimal. I know this has been a very long journey to just display some numbers, which obviously could have been done with a line or 2 of code, but I really enjoyed learning about and experimenting with all this stuff, so I hope you found it interesting as well. In any case, behind the scenes I've quickly gone and added a 4-bit version of all of this to our 4-bit register, which again will upgrade to 8 bits and probably more in the future, but for now if we store for example 1111 in there, we can see the number 15 being displayed. And I hacked in a tiny toggle here, so if we want to interpret this as a signed value using the 2's complement representation, we can do that very easily. Hopefully this ability to visualize the data we're working with is going to make our lives a lot easier as we continue tinkering and trying to eventually build a little computer inside the simulation. That's all for now though, so until next time, cheers.